Okay, hello and welcome to my channel. Today we're gonna talk about the resonance and quasi-bound states in quantum mechanics. Okay, so let's start by taking a look at the finite square well potential, and this time we're going to take a look at scattering states. Okay, and your energy would be greater than V naught, so that would be a scattering state. Okay, so with a scattering state, what you have is that when you send in a wave, here is going to be a reflection point, so there would be something that reflected here, something that transmitted through, and to here there's going to be another point where something is going to be reflected and something is going to go through. Okay, so I'm going to use write it like this. Here is our take AE to IKX. Reflected would be BE to minus IKX. So we're going to take 3 regions, and with each region we're going to have a different K. So I will write this as K1, and here B, A, B, C, C, E, this is gonna go that K2, D, E to the minus. Yeah, sure. X, go back. And in this region here, it doesn't have any reflection point for the wave to bounce back. Therefore, it's only gonna have one wave that will go through, and I cannot use E, so next is F. And this has the same potential as the first region, so that would be our K1. Right, and with this, the energy is greater than 0, of course, and K1 is K1 square, H bar square, E. This is minus V naught, as this is a well we're looking at, E plus V naught. Right, so there we go, we have that. Next is the coefficients that we have. The reflection coefficient is B over A, same K, and for transmission, F over A, because, well, this region has the same K as the first region, so it doesn't need any ratio. And next would be the answer for your transmission coefficient, which I think I wrote is T1 plus 1 over 4, so V naught square, E times E plus V naught, sine square of K2A. I believe that is correct. Oh, I forgot 2 here. Alright, so the bound for 1 over T is 1. Okay, so when you take your E and let it go to 0, your T would subsequently go to 0. And next, if you have your T and you let it go very large, this would go to 1. 1. Meaning that it would go through like there are no potential at all. So that is called perfect transmission. Okay, so Now we're gonna evaluate the inside of the sine function here, as we can put this into something more neat. Because, well, immediately you can see that our inside of the sine here have a K2A. And if you remember about Ka, you can put that into unit-free numbers. And in this case, we can put it with K2 is E plus V naught. So time in, you can factor out V naught and divide. So writing that would be 2mv naught a squared. We're gonna root that later. Plus 2mv naught a squared e over h per square. You root this, but I don't want to deal with this as it is kind of messy and the energy still has a unit here. So we would want to put our energy to the dimensionless version of it. We do this by factoring out the 2mv naught a squared over h per square. This would give us, here is 1 plus e, you don't have v naught here, so you would have to put in v naught, a 1 over v naught. So that would give you 2m v naught a squared. Why? Yep. 1 plus e over v naught. Okay, so this would be the form I want to deal with. And this, you might recognize, is z naught squared. And this is the dimensionless version of your energy. We will call this the little e. Okay. So now you have that. You can put it in. Since this doesn't really matter, you can sub it out. So you get 2z naught squared root 1 plus e. Right, and now we would want to continue and look for the perfect transmission. So if you want to, you can sub what you got here back into our 1 over t. And you would get something that is, well, probably easier to deal with than what you have here, as what you have now is completely filled with unit-free numbers. But that derivation, I don't think I written that down. So we're just gonna skip that, and if you want to, you can do that yourself. Now we're gonna continue to the condition for perfect transmission, which would require your this part here. So for perfect transmission, t equal to 1. So this part, what you have here, have to be 0. So for that to happen, you need whatever inside of your sine function to be equal to a multiplet of pi. So here we're gonna take this guy instead. So 2z naught squared 1 plus e equal to multiplet of pi. And this would give you your e, which is minus 1 plus n squared, pi squared over 4z naught squared. Okay, so with what you have here, now you sub it back to get your big E. So this would turn into, this is pretty important, as this is our final solution, is minus V naught plus n squared pi squared h bar squared 2ma squared. Alright, so this is your final solution, and you might recognize this as the energy eigenvalue for the infinite square well potential, and that is exactly that. So we're gonna go back to this picture right here and see. What you want to imagine now is that, suppose this is your system, you would want to imagine or stack infinite square well potential onto your finite square well potential, right? So imagine this goes to infinity. So you stack that on. And the condition for resonance is that if your energy of the system is equal to the energy eigenvalue of the infinite square well potential that you stacked on top, meaning that your E of the system would be the same as the energy eigenvalue of infinite square well potential. This guy is n squared pi squared h bar squared over 2ma squared. Right. So that would be one condition for resonancy. Subsequently, from this guy equal to multiplet of pi, we can again take a look at this guy. So take this guy to be a multiplet of pi. You can find that, well, from this, your your width, your width you take here is 2a. Right, yeah. Width you take here is 2a. So some minor change here. This would be 2a squared. That is 2a squared. A squared. As you take that to be minus a to a, well, that explains the 2 here. I overlooked that part. Okay, so with this, you can figure out that the width of your well have to be equal to a multiplet of the half wavelength. So that is another condition for resonancy. Okay, and from this resonance part and perfect transmission, there is a discovery that is called the Ramsauer-Townsend phenomena. Find somewhere to write that. Here it is. So the Ramsauer-Townsend phenomena is found by scattering, well, yeah, doing elastic scattering of a low energy electron on noble gas. So Ramsauer Townsend phenomena. Yeah. So what they do is that they conduct elastic scattering with low energy electron on rare gas atoms. So, and what they get back is something like this. The reflection coefficient and your dimensionless E, take this to 1, and as they increase the energy, they notice there is a dip, and then it goes back up. And in this dip, I believe is 1 eV. And if you continue to draw out, the shape is something like that. So they notice there is a dip when the energy is still not large enough for it to happen. And that is basically where the energy of the system matches an energy of an infinite square well potential, an eigenvalue of the infinite square well potential that is, you imagine it to be stacked on top of your system. So that is the Ramsauer-Townsend phenomena. The conclusion is that the reflection coefficient is a proxy for scattering cross-section. So basically all you have to remember is this picture right here. This is where the resonance happen. This go on, all right, and to a point it's going to go flat, meaning the particle is just going to go through like there are no potential there, right? And yeah, I believe that is it for the resonance part. Now I would want to make a brief talk about the quasi-bound states. Okay, so this could be useful later on. So today just going to be a definition of quasi-bound states. So suppose you have some potential like say this, okay, and with this potential here, there would be bound states here, right? And resonance might happen eventually when you do trial and error with your energy, and it eventually is gonna match with an eigenvalue. Then resonance is gonna happen, and the energy eigenstate of this is gonna shoot up to this level, making it, well, quasi-bound states. These are quasi-bound states. Okay, and these are bound states. These are bound states. And that is the definition of quasi-bound. It has a definite lifetime, of course, because the potential out there, it can potentially leak through, and it's not stable. It will die. I think the lifetime of a quasi-bound state is h bar over the half width. And you will see this again in like probably the Breit-Wigner part, but that is it for the quasi-bound state. I think it is interesting, so I really want to share it. Okay, so that's it for today. Goodbye.